Today we will look at Lesson 6E, Polynomial Theorems. In this lesson, we will be learning 4 different polynomial theorems. The first theorem we will be learning is called the remainder theorem. What is the remainder theorem? Let's look at the definition here. When a polynomial p of x is divided by x minus k, its divisor, until a constant remainder r is obtained, then this r is the remainder of this polynomial function when it's divided by x minus k, and this remainder equals p of k. Let's look at how we can justify this conclusion. When using remainder theorem, it is important to realize the following statements are equivalent, but those statements are kind of justification on this conclusion in the remainder theorem. We have already learned the division statement in 6C. When we have any polynomial, when we divide this one by its divisor x minus k using the long division or synthetic division, we can get the quotient. This quotient is a function of x. Then there's a remainder if this one cannot be divided by its divisor evenly. So you can go back to look at the examples we did in 6C. So the remainder, this is called the division statement. The division statement is any polynomial equals the divisor times the quotient plus the remainder. When I have the 0 of the divisor, I replace this x with the 0 of the divisor. I can have p of k. So if I plug the k value into the right side, I can have k minus k times q of k plus the remainder. Since k minus k is 0, 0 times anything is 0, so this one will become 0 plus r. This one means p of k equals r. That's the remainder. This reason why in the remainder theorem we can conclude remainder always equals p of k. K is the 0 of the divisor. P of x divided by the divisor x minus k leaves a remainder of r. Let's apply the remainder theorem to solve example 1. Find the remainder when 2x to the power 4 minus 3x cubed plus x minus 4 is divided by x plus 2. Of course, you still can apply the long division or synthetic division method to find its remainder. But remainder theorem gives us a more efficient way and a quick way to find its remainder. We only need to find the 0 of this divisor. So the 0 of the divisor is negative 2. I only need to use negative 2 to replace x in the polynomial function. P of negative 2 must be the remainder. What is p of negative 2? Let's plug negative 2 in for x. So it's 2 times negative 2 to the power 4 minus 3 times negative 2 cubed plus negative 2 minus 4. Let's calculate based on the bad math. So we can have 32 plus 24 minus 2 minus 4 equals 50. So when this one is divided by x plus 2, the remainder must be 50. You also can justify this solution by using long division or synthetic division methods. Let's look at example 2. When a p of x is divided by x squared minus 3x plus 7, the quotient is x squared plus x minus 1, and the remainder r of x is unknown. When a p of x is divided by x minus 2, the remainder is 29. When a p of x is divided by x plus 1, the remainder is negative 16. Find the remainder of x in the form of ax plus b. When reading the question, some students will be confused about this problem. Let's try to understand this problem correctly. This p of x is the same for both of the conditions. When a polynomial is divided by a linear binomial, the remainder should be a constant based on the remainder theorem. But when a polynomial is divided by a quadratic, its remainder could be a linear expression. The degree can be 1 less than the divisor or maybe a constant. So needs to understand this one correctly. This reason why the question is correct. So based on those conditions, you need to look for when this p of x is divided by a quadratic. What would be the remainder in terms of x? And this remainder should be 1 degree less than this one, or maybe it's just a constant when a equals 0. How can we solve for this remainder when the p of x is divided by this quadratic? Based on the first condition, we can know p of x must be equal to the divisor times the quotient plus the remainder. So right now, we let the remainder be ax plus b. Based on the second sentence, this p of x is divided by x minus 2. The remainder is 29. So what does that mean? P of 2 is 29. We have already assumed the polynomial function model. What is p of 2? We can just sub this 2 for x in this assumed polynomial model. So p of 2 should be 2 squared minus 3 times 2 plus 7. 2 squared plus 2 minus 1 plus a times 2, 2a plus b. So this one equals 29. We can simplify this equation into 2a plus b equals 4. The third sentence is, if this p of x is divided by a linear binomial again, x plus 1, the remainder is negative 16. We can use the remainder theorem again. So p of negative 1 should be negative 16. We replace x in this polynomial model with negative 1. So we should have negative 1 squared minus 3 times negative 1 plus 7 times negative 1 squared plus negative 1 minus 1 plus we should have negative a plus b. If we simplify this equation, we can get negative a plus b equals negative 5. And these two equations will form the system of two equations. We can use substitution or elimination methods to find the a and b values. So we solve the system of two equations. We can have a equals 3, b equals negative 2. And therefore, the remainder we are looking for is 3x minus 2. This time we need to look at the second polynomial theorem, which is called the factor theorem. What is the factor theorem? Let's look at the definition here. For any polynomial p of x, k is a zero of p of x, if and only if x minus k, this divisor, is a factor of p of x. What does that mean? So the zero of the divisor can make this p of x equal 0. This one suggests this polynomial function can be divided by this divisor evenly. There's no remainder. Remainder equals 0. If the remainder equals 0, this divisor must be a factor of the polynomial function. Let's look at example 3. Find k given that x minus 2 is a factor of this polynomial function. Hence, fully factorize this polynomial function. We need to determine the k value before we can factor this cubic polynomial function. How can we determine the k value? We are given the condition that this linear binomial is a factor of this one. Based on the factor theorem, the zero of this divisor, which is 2. So p of 2, which is the remainder based on the remainder theorem. But right now, this remainder must be 0. Otherwise, x minus 2 cannot be a factor of this cubic polynomial function. So, based on p of 2 equals 0, we plug 2 in for x. We can have 2 cubed plus k times 2 squared minus 3 times 2 plus 6 equals 0. Let's solve for k. We can have 8 plus 4k minus 6 plus 6 equals 0. Therefore, 4k equals negative 8. K equals negative 2. Therefore, the polynomial function is determined. This p of x is x cubed minus 2x squared minus 3x plus 6. Let's fully factorize this cubic polynomial function. But anyway, we know one factor of this cubic polynomial function already. So we can say this 1 can be factored into x minus 2 times another factor first. So what is the other factor? We can use the long division or synthetic division to find the other factor. We also can just use the method we introduced in 6D to determine the other factor. X times this one must produce the leading term. So what is the leading term? X cubed. So x times what is x cubed? It's x squared. Then negative 2 times this last must produce the constant in the polynomial function. So negative 2 times what will give me positive 6? That should be negative 3. The only missing term is the middle term. I don't know the middle term. So I can say x squared plus mx minus 3. Then I can expand this binomial times this trinomial to make two polynomials equal in order to find the m value. This is the method we learned in 6D. But you also can just use long division or synthetic division to find this factor. So this time we try to review the synthetic division. I will use the synthetic division. So it's 1, negative 2, negative 3, positive 6, since there's no missing term in the polynomial function. Put down the 0 of the divisor. Bring down 1, multiply them. Add them up. Multiply these two. Add them up. Multiply these two. Add them up. The remainder is really 0. And those values are the coefficients of this factor. So p of x can be factored into x minus 2 times x squared minus 3 first. As for this quadratic, it's easy to be factored further. So x squared minus 3 can be factored into x plus root 3 times x minus root 3. So right now, you need to know how to apply different ways to solve this problem, including the polynomial equality, long division, synthetic division, to find another factor when you factor a high degree polynomial. So right now, let's look at the most important theorem that we need to learn in this lesson. And this is the fundamental theorem of algebra. The first statement in the theorem is every polynomial of degree n is greater than or equal to 1 has at least one zero, which can be written in the form a plus bi, where a, b are real numbers. If the polynomial function p of x is a polynomial of degree n, then p of x has exactly n zeros, some of which may be either irrational numbers or complex numbers. For real polynomials, we also need to extend our knowledge to those following statements. Every real polynomial of degree n can be factorized into n complex linear factors, some of which may be repeated. This one is corresponding to b. So for a polynomial, with degree n, this polynomial can have n zeros. N zeros means you can have n complex linear factors. Every real polynomial can be expressed as a product of real linear and real irreducible quadratic factors. So since there are n complex linear factors, so we can change any real polynomial into the product of those n linear factors. Every real polynomial of degree n has exact n zeros, some of which may be repeated. So the number of the zeros is the same as the degree of the polynomial. If p plus qi, q cannot be 0, is a zero of a real polynomial. So if q is not 0, this one must be a complex number. If this complex number is a zero of a polynomial, then its conjugate, its complex conjugate, p minus qi, is also a zero. So p plus qi and p minus qi must occur in the zeros of a polynomial function at the same time. Every real polynomial of odd degree has at least one real zero. So for example, like a cubic polynomial function, it must have 3 zeros. Once the complex zeros have to occur in a pair, so the third value, the third zero, must be a real root, a real zero. Let's look at how we can apply the fundamental theorem of algebra in solving the problem in example 4. Let's look at example 4 first. Suppose negative 3 plus I is a zero of a cubic polynomial function, where a is a real number. Find this a value and hence find all zeros of this cubic polynomial function. Based on the fundamental theorem of algebra, if negative 3 plus I is one complex zero of a real polynomial function, then its conjugate must be another zero. So negative 3 plus I is a zero, the other zero must be negative 3 minus I. When you have the complex zero, the conjugates must occur as a pair to be the zeros of this polynomial function. Since we know both negative 3 plus I and negative 3 minus I are the zeros of this cubic polynomial function, we can rewrite this polynomial function as x minus negative 3 plus I times x minus negative 3 minus I. This linear factor times this linear factor should produce a quadratic factor. A quadratic factor must multiply by a linear factor again to get a cubic one. So the last factor must be a linear factor. That's the reason why I write down mx plus n for the last linear factor. So right now, we need to expand the product of those 3 linear factors in order to apply the polynomial equality to find the missing values of a and m and n. In order to expand these 2 linear factors in the product quickly, just as what we did in 6D, we can apply the knowledge we knew already. So this quadratic can be obtained by this way. X times x is x squared. But what is the x term? I only need to add these 2 zeros up. I can get a negative 6. So opposite to this negative 6, which is 6, the 6 must be the coefficient of x term. As to the constant, I only need to multiply these 2 complex zeros up. So negative 3 plus I times negative 3 minus I is 9 minus I squared. I squared is negative 1. 9 plus 1 is 10. So that's how we can expand the product of 2 linear factors quickly. Then this one multiplied by the last linear factor to get a cubic polynomial function. Based on 6D, we are supposed to expand these 2 polynomials in the product as well. Then we equate the corresponding terms to find the missing values for a, m, and n. However, we also can use our logical reasoning to cut down the workload a little bit, because we know x squared times this mx must produce ax cubed. So we can know that this m is the same as a. And this last constant times this last constant, they multiply to be negative 30. So 10 times negative 3 is negative 30. I can know this n value must be negative 3. In this case, I can cut down 3 unknowns to 1 unknown. And it's also easy for me to expand these two without m and n. So let's expand the product of these two polynomials and combine the like terms. So the result of the expanded form is ax cubed plus 6a minus 3x squared plus 10a minus 18x minus 30. This polynomial equals this polynomial. We only need to equate the corresponding terms to find the missing value a. So we can have 9 equals 6a minus 3. Or we can have a equals 10a minus 18. You can use either of these two equations to find the a value. Anyways, a value should be 2. So after we find the a value, this polynomial function has been determined. This polynomial function is 2x cubed plus 9x squared plus 2x minus 30. The zeros, the first one is negative 3 plus I. The next one is negative 3 minus I. The last one should come from this linear factor, which is 2x minus 3. Let 2x minus 3 equal 0. We can have 3 over 2. Let's look at how we can solve the problem in example 5. 1 0 of a cubic polynomial function ax cubed plus a plus 1x squared plus 10x plus 15. A is a real number, it's purely imaginary. Find a and the zeros of the polynomial. Since we are given 1 0 of this cubic polynomial function, we can let the purely imaginary zero be bi. Of course, b cannot be 0. Since this cubic polynomial function has 1 0 bi, which is a complex 0, we can know this polynomial function must have its conjugate as another 0, based on the fundamental theorem of algebra. Therefore, this original cubic polynomial function can be written in the form of x minus bi times x plus bi. And these two will multiply to be a quadratic expression. The quadratic expression must be multiplied by a linear binomial to get a cubic polynomial function. So we can let this linear binomial be mx plus n. Let's expand these two linear binomials. So x minus bi times x plus bi can produce x squared plus b squared. Then times mx plus n. Of course, you can keep m and n and expand the right side. So then you only need to equate the corresponding terms based on the polynomial equality to find the missing values for a, b, m, and n. But I prefer to use logical reasoning to rewrite this mx plus n in terms of a and b. Just like what we did in example 4, we know this x squared times mx should produce ax cubed. So this mx must be ax. And the last times last must produce 15. Therefore, we can say b squared times n equals 15. So n is 15 over b squared. Then let's expand the product of these two brackets. So we can have ax cubed plus 15 over b squared x squared plus ab squared x plus 15. Let's equate the corresponding terms. So we can have a plus 1 equals 15 over b squared. And 10 equals ab squared. Let's use substitution or elimination method to solve the system of two equations. For the first equation, we can multiply both sides by b squared. We can have ab squared plus b squared equals 15. So for ab squared, this one is just 10. So we can sub this 10 in for ab squared. And therefore, we can find the b value. So the b value will be positive or negative square root of 5. After we find out the b value, we can find the a value. So the a value, a plus 1 equals 15 over b squared, or we can use 10 equals ab squared. So b squared is 5. 10 divided by 5, anyways, a equals 2. Therefore, the original cubic polynomial should have those three zeros. One is positive root 5i, negative root 5i. This is the second one. And the last one should be 2x plus 15 over 5, which is 3. So the last one should be negative 3 over 2. Right now, let's look at the fourth theorem we need to learn in this lesson. We need to look at the sum and the product of roots theorem. For this theorem, we have already touched in 1c, where it's called the sum and the product of roots for a quadratic equation. For a quadratic equation, ax squared plus bx plus c equals 0. Of course, a cannot be 0. The sum of the roots is negative b over a. The product of the roots is c over a. So right now, we can generalize this theorem to any polynomial equation with the real coefficients. For the polynomial equation, in the standard form, an x to the power of n plus an minus 1x to the power of n minus 1, all the way down to a2x squared plus a1x plus a0 equals 0, an cannot be 0. Otherwise, the highest degree n will disappear. So remember, your an is the coefficient of the highest degree. An minus 1 is the coefficient of the second highest degree of this polynomial equation. This series on the left side also can be written in the sigma notation. We have already introduced this one before. So sigma r starts from 0 all the way to n. ar x to the power of r equals 0. So this is a kind of more concise expression for this left side. Even for this degree n, we still have the sum of the roots. The sum of the roots, based on the fundamental theorem of algebra, we know this equation should have n zeros, n roots. So for those n roots, if you add all of them up, the sum is negative an minus 1 over an. And the product of these n roots is negative 1 to the power of n times a0. This is the coefficient of the constant term divided by an. So here, there is a little bit of mistake that we need to correct. The product of the roots for the quadratic equation should be c over a rather than c over x. Right now, in example 6, let's apply the sum and the product of the roots theorem to find the sum and the products of the roots for this polynomial equation. Let's look at the highest degree is 3. The coefficient of x cubed term is a3. So this x squared term should be a2x squared. So the coefficient of a2 is negative 7. And a1 should be positive 8. The constant term should be a0. So based on the theorem we just introduced, so the sum of the roots, this polynomial equation can have up to 3 roots. They may be repeated. The sum of those 3 roots should be negative an minus 1. In this case, an minus 1 is a2 divided by an. In this case, an is a3. So the sum of all those 3 roots should be 7 over 2. And the product of those 3 roots should be negative 1 to the power of n. So right now, the degree of this polynomial equation is 3. So we change the n to 3. Then times a0. a0 in this case is negative 1 divided by an. an here is a3 divided by 2. Therefore, the product of those three roots is 1/2. Let's look at the last example in this lesson, example 7. A real polynomial has the form p of x equals 3x to the power 4 minus 12x cubed plus cx squared plus dx plus e. The graph of y equals p of x has y-intercept 180. It cuts the x-axis at a 2 and a 6, and it does not meet the x-axis anywhere else. Suppose the other two zeros are m plus minus ni. N is greater than 0. Use the sum and the product formula to find m and n. This is a long problem. Therefore, we need to really analyze what we are given, what we need to look for. Let's analyze the first condition we are given. The first condition is this polynomial is a quartic polynomial. So if we let this polynomial be 0, we can turn this polynomial function into a polynomial equation. This equation must have 4 zeros, or we can say 4 x-intercepts, if possible. The graph of y equals p of x has y-intercept 180. This is the second condition we are given. How can we find the y-intercept? We only need to let x be 0. If x is 0, this is 0 minus 0 plus 0 plus 0 plus e. So in this case, p of 0 is e, and this e is the y-intercept. And y-intercept is 180. This one tells me e value equals 180. Let's look at the third condition. It cuts the x-axis at 2 and 6. 2 and 6 are the zeros and does not meet the x-axis anywhere else. This one suggests the other two zeros must be imaginary numbers. So I can let the other two zeros be n plus ni and m minus ni. If two imaginary zeros occur together, they must occur in a pair, in a conjugate pair. This reason we can understand why the question supposed the other two zeros as m plus minus ni. Since this polynomial function is a quartic one, if we rewrite this polynomial function in the factored form, this polynomial function must have 4 linear factors. We can rewrite this p of x as x minus 2 times x minus 6 times x minus m plus ni times x minus m minus ni. Also be careful about the leading coefficient. This quartic polynomial function has a leading coefficient 3. But if I just change the p of x to this factored form with 4 linear factors, I should multiply by 3 in the very front to show the leading coefficient. So right now we need to apply the sum and the product of the roots theorem to find the missing values m and n. The sum of these 4 roots, 2 plus 6 plus m plus ni plus m minus ni. Those 4 roots should add up to negative an minus 1 over an. So an minus 1 is negative 12. An is 3, which gives us 4. And the product of those 4 roots is 2 times 6 times m plus ni times m minus ni is negative 1 to the power of n. In this case, the n value is 4. The constant term, which is e, and the e value has been found already, which is 180, divided by 3. So this one can be simplified into 60. The sum of those 4 roots can be simplified into 8 plus 2m equals 4. Therefore, we can solve for m. So m equals negative 2. The product of those 4 roots also can be simplified. So it should be 12 times m plus ni times m minus I should be m squared plus n squared equals 60. And this m squared right now is negative 2 squared, which is 4. Therefore, 12 times 4 plus n squared equals 60. Let's solve for n. So 4 plus n squared is 5. And n squared should be 1. N can be positive or negative 1. But based on the restriction given, n has to be greater than 0. So we only can take n equals 1. That's how we can find the m and the value in this question. And this is the end of the lesson.